All right, we've learned about state equations. We've learned about calculus. Now let's see what we really can do. This is where the good stuff starts. Well, it's all good, but it's going to get even better. Check this out. We're going to learn about equilibria and stability today, and we're going to start in one dimension because we have a lot of really great tools available to us when we do this in one dimension. Okay, so let's talk about equilibria first. What it means for a system to be in equilibrium is that it's constant. It's not changing anymore. And that occurs when x prime is equal to 0. So when x prime is equal to 0, that means the system is in equilibrium. System in equilibrium. Okay, so think about that in terms of what you've learned so far in calculus. If I said the derivative of a function is equal to 0, what is the function? It's a linear, exponential, sinusoidal function. If the derivative is equal to 0, it's a constant function. Exactly. And that's what we were just saying it means to be in equilibrium. 6 is in equilibrium. That means over time, x of t is always equal to a constant. That's why it's derivative 0. Okay? So when we're looking for equilibrium points in a system, we're going to look for the values of x that cause x prime to be equal to 0. Let's take one of our simplest examples, which is our classic type of linear feedback, where x prime is equal to rx. This, in terms of ecology, is the same thing as saying that x prime divided by x is equal to r, so we have a constant per capita growth rate. Another way to say it is that the rate of change of this function is directly proportional to the current state of the function. And so hopefully now you're thinking, that sounds like an exponential. From what you know about calculus, what kind of function's derivative is equal to the original function or is directly proportional to the original function? Those are exponential functions that solve those out. Right. But what does that have to do with what I just said about equilibria? What we're going to do is we're going to look for the values of x such that the expression rx is equal to 0. Okay, so when is the system in equilibrium? Right when x prime is equal to 0, right? So we have to solve for when rx is equal to 0. If we solve for where x prime is equal to 0, so we set whatever's on the right-hand side as a function of x is equal to 0 and solve that for x, those are going to be the equilibrium points of the system. And so just dividing both sides by r like that gives me the conclusion that x equals 0 is the only equilibrium point of the system. That's going to be the same kind of method that I'm going to use in general. If x prime is equal to a general function, f of x, I'm always going to try to solve for where is f of x equal to 0. For what values of x is the rate of change going to be 0, and that's going to get me the equilibrium points. Now let's talk about stability. Okay, so for stability, there's two main types. There's what we call stable, and that's versus unstable. Okay. Does that sound like anything that's going on right now? Some things are stable, some things are unstable. Think about what that means in general. Stable things attract and they stay calm, right? It's all converging to that thing. Unstable things are really wild and things are diverging from that place. And that's the same thing that we're going to talk about in the system dynamics here. Once we find the fixed point, we want to know if it's going to be classified as stable or unstable. And that's going to have to do with whether nearby trajectories are attracted to that stable fixed point or are repelled away from that unstable fixed point. The easiest way to see this for me is to use some sort of visual aid. And the visual aid that we're really going to focus heavily on in one dimensions is this wonderful graph where we actually graph x versus its derivative x prime. This is a real winner. And like I said in some of the earlier weeks, this is really great that we can do this in one dimension. The reason that we can create this graph in one dimension is because in one dimension, our state space is one dimensional. here's our state space, the x-axis. And so the tangent space as well is also one-dimensional, and 1 plus 1 is 2, so we can make a two-dimensional graph that visualizes the rate of change versus the state. We're not going to be able to do this in 2 dimensions because that would be 2 plus 2 or 4 dimensions, and I can't really graph that. So in 2 dimensions, this is analogous to looking at all the arrows of a vector field, but in 1 dimension, we actually get to graph exactly what the function f of x is, comparing it with the state value x. Okay, so let's say that, like for our example right now of exponential growth, where the rate of change is directly proportional to current state, we're going to graph the function rx. I can't really graph this unless I know what r is, so let me at least assume some sort of general property for r. Let's say maybe r is greater than 0. Okay? If r is greater than 0, what I'm graphing right here is a linear function that has a positive slope and goes through 0, 0. So that's a graph of f of x. Okay, this is not a graph of the solution. That's very important for you to understand. This is a graph that allows us to see what the rate of change is doing as a function of the current state. It is not illustrating that the solution is linear. In fact, what we just learned in calculus is that the solution to this is exponential equations. Okay, so I'm not graphing the solution. Time is only implicitly spoken to in this graph, and I'm not explicitly graphing time. But what I want to know is, I just learned that the one fixed point for this equation is x is equal to 0. Okay, that's right here. So that's going to be my one and only equilibrium point for the system. What I want to know is, if I start somewhere else, let's say I start over here with a state that's positively valued and away from 0. What's going to happen to that system if this is my initial condition? Is it going to go towards the fixed point, or is it going to go away from the fixed point? Luckily, the rate of change is being graphed right here. So if I think about maybe this, maybe I'm going to assume that this is my initial condition. This is my initial condition here. Okay, if I start right here, all I have to do to wonder where I'm going to go is look up and say, hey, if you start here, what is your rate of change doing? Is your rate of change increasing? Is your rate of change positive, which would result in a behavior where you're increasing? Or is your rate of change negative, which would result in a behavior of your state decreasing? Here's my initial condition here. And when I look up at the visual, that tells me what the rate of change is, tells me the rate of change is positive. So if I'm sitting right here as my initial condition, think about Euler's method too. If I was doing Euler's method, I would say, okay, I'm starting here. What's my rate of change? I'm going to make a little step in that direction. Starting right here, my rate of change is positive. So if my rate of change is positive, I'm going to go that way. And then if I end up over here, my rate of change is still positive. So I'm going to go that way, and I'm going to go that way. And so what it tells me is that x is going to always be increasing if I start with x greater than 0 to begin with. Because for all the values of x greater than 0, the derivative, the rate of change, is always positively valued, and that always results in increasing behavior. So even if I start really close to 0, what's going to happen? Will I go to 0 then? Nope, my rate of change is positive, so I'm going to continue flowing in the right direction. I mean to the right, not like the correct direction. What if I start over here? What if I start a negative territory with a negative x? Is my rate of change, if I start over here, what if I start here, is my rate of change going to be positive or negative if I start over here? Again, looking at the graph, my rate of change is a negative value. So if I start with negative x, I'm going to get more negative. And if that's negative, I'm going to get more negative, more negative, more negative. So if I start here, I'm going to be flowing in that direction. Okay? So x is increasing if I start with x greater than 0. And likewise, x is decreasing if I start with x less than 0. Now going back to stability, I kind of want to classify this fixed point right here. What I'm trying to do is give a descriptor to this equilibrium point. Either it's going to be stable if initial conditions are attracted to it, or it's going to be unstable if initial conditions just want to get away from it. They're repelled by it. And which situation do you think we're in for this case where r is greater than 0? It's unstable. It's unstable because if I start to it on this side, I'm going away from it. If I start near it on this side, I'm going away from it in the other direction. So it's repelling initial conditions from both directions. And so the resulting conclusion is that x equals 0 is an unstable fixed point. An unstable equilibrium point. Sometimes it's called a fixed point in some literature, sometimes called an equilibrium point. Equilibrium means that it's staying at a constant value. Fixed means it's staying at a constant value. So sometimes I might use the verbiage fixed point. Either way you slice it, this is an unstable one because it's repelling everything that even starts close to it. They just want to get away from that fixed point. Now, does that align with what I know, what I just learned from calculus? Remember, we just went through all this calculus and we talked about solutions to the equation x prime is equal to rx. Does anybody remember what the actual time solution is? Like what's x of t for this equation? X of t, let's see. So we're talking about x prime is equal to rx, right? What is the function x of t that solves the state equation x prime is equal to rx? Oh, geez, you just learned this. It's exponential growth at the rate e to the rt and starting with the initial condition x naught. So the actual full solution is x naught e to the rt. And like we were just saying over there, we're staying with the assumption that r is positive. So we're assuming for the illustrative purposes over here, we're assuming that our r is a positive rate. And so now, let's try to graph a time graph of what the solution looks like. Okay, and this really doubles down on the emphasis that this graph over here is not the solution curve. This is not a time series graph, but it tells you something about time series graphs. And so that's what I want to tie in right now. It's how those two things are related. Okay, remember what I said, let's start with this initial condition over here, some positive x. And if I do start here, what x prime is telling me to do is to make moves further in the right direction, move to the right and continue increasing. Well, if I assume that r is greater than 0 and I talk about starting at an initial condition x naught, which is greater than 0, so let's say that that's at x naught over here. Same thing as saying that this initial condition x naught is positive over there. What's going to happen when I graph this solution? What does that look like when r is greater than 0? It looks like that. It looks like exponential growth. And the fact that this curve is going up and up and up is the same thing that this arrow is telling me when it says go right, 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 right. What about over here where I started to the left and it said go left, 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 left? What does that mean over time? Well, if I start here for this x naught, that would mean I'm starting with a negative initial condition. Okay, so to tie it in with what's over here, that one there would be some negative initial condition. Okay, so this x naught here is me starting over here in this negative territory, but I'm still growing at an exponential rate. But what does exponential growth look like when you're multiplying it by a negative number? It looks like exponential growth in the downward direction. Okay, so either way you slice it, this is going to be exponential growth. Either it's going to get really, really big positive if I started with something positive, or it's going to get really, really big negative if I started with something negative. Where's the equilibrium point on this graph? What was the equilibrium point again? All right, there's my equilibrium point. My magical point, x is equal to 0, was my one and only equilibrium point for this model. And where that appears on the time graph is right here. It is the t-axis because it is the value of x equaling 0 forever. So what I'm trying to draw, which I'm drawing it over a black line, is this is equilibrium. That would be the one and only equilibrium solution. If I start with nothing, I'm not going to change at all. But you can see that if I start away from nothing, even if I start close to it, but if I start with a little bit of positivity, that's going to increase. If I start with a little bit of negativity, that's going to decrease. So everything is getting repelled away from this equilibrium point, and that's why we call this an unstable equilibrium. So this is the unstable equilibrium point, x equals 0 in time. Cool. Let's try that all again, but let's flip the switch and now assume that r is less than 0, and we'll see what happens for the other type of stability. Okay, so let's erase pretty much all of that stuff, but the solution remains the same, whether r is greater than 0 or less than 0. And then let's get rid of this whole graph here, and let's replace it with a graph where I'm going to assume that r is now a negative number instead of a positive number. Now, while you're watching me erase the whiteboard, why don't you try to graph the graph you think I'm going to draw right here, x prime versus x, but now we're going to assume r is less than 0 instead of greater than 0. So now we're going to make the new assumption. We're going to assume r is less than 0 now. And what would your graph look like on the x versus x prime graph? We're still talking about graphing this function. We're graphing f of x. Okay, f of x is equal to x prime. F of x is what's defining the state equation. But now we have a negative slope. We still have a line that's going through 0, 0, but now the slope is negative. So what does that look like? Right, it looks like this. It's a line going through 0, 0, but now it has a negative slope because the r is less than 0. Okay, nevertheless, the fixed point is still the same. If I ask the question, where does f of x equal 0, the one and only answer is where x is equal to 0. So the fixed point, the one and only equilibrium point, is still just right there. But now let's analyze the stability by considering ourselves starting somewhere else in the state space. Maybe we're going to start over here. Maybe this is our initial condition, which I'll abbreviate with IC now. IC is for initial condition. And if I started over here, my x naught right here, what would my state equation tell me to do now? Is it going to tell me to increase because my derivative is positive, or decrease because my derivative is negative? If I start here, you can see that the output for the rate of change is negative. And so if I do start here, it's going to tell me to decrease, decrease, decrease. What happens when I hit this big black dot right here? Am I going to still decrease? No, I'm going to stay the same, because on this black dot, it's telling me my x prime is 0. So it's telling me now to stop changing, because my rate of change is 0 here. What if I start with an initial condition on the negative side? What if I start with some initial condition on this side over here with this x naught? Is my rate of change going to tell me to increase or decrease? All I have to do is look up at the graph. My rate of change says that it's positive. X prime is positive, so I should increase. So if I'm starting in negative territory, I should increase, increase, increase. Oh, wait, hold on. Rate of change is 0 there. Better stop right there. Okay? And so you can see that if you start on either side of the equilibrium point in this case, things are attracted to the fixed point. They're going towards the fixed point, as opposed to our other case where things were getting repelled away. And so when we assume that r is less than 0, we find ourselves in the other situation, stability-wise, where now the equilibrium point x is equal to 0 is a stable equilibrium. It's a stable equilibrium point because now things are attracted to it rather than repelled by it. Cool. So this fun graph here, where really, look, the phase line part of it is right here. Here's the phase line describing that I'm going towards the equilibrium point. It tells me a lot about the stability. It tells me where I'm eventually going to go. What it doesn't tell me is it doesn't tell me exactly how fast in time I'm going to go to get there, right? Because I don't see time explicitly displayed on this graph. And so that's why we come over here to compare that or line that up with the time series graph. We're really lucky to be in a situation for this type of model, x prime is equal to rx, because this has an explicitly found solution. That's not true of all models. Most models actually don't have an explicit solution that you can just say, oh, here's the answer. That's a really special thing, and it happens when the models are linear in nature, and so that's cool. And it really helps me to graph the time graph because I can like see the function of t right here, and so what I was talking about over here, I can match up on the time graph. Let's start again with our positive initial condition. Remember we said that if we start with a positive amount of x, our rate of change being negative is going to tell us to go towards the equilibrium. Okay? What if I graph this with a positive initial condition? What if I told you to graph the function e to the minus t, or e to the minus 2t, or some other rate where the exponent here is a negative number times t? You wouldn't graph exponential growth anymore. You would end up graphing exponential decay, right? And so you can see that my solution is asymptotically approaching 0. This downward behavior as it tends towards 0 is the same thing that I was talking about when I was drawing these little arrows saying, go to the left, go to the left, go towards 0. That's exactly what's happening. But on the time graph, you can see it explicitly as a function of time. Okay? You can see that the function is decreasing at every moment, always decreasing towards 0. The fact that it's always decreasing is the same thing as observing that its rate of change is always negative in this territory. And the opposite is true in the negative territory. So if we start with a negative x, if we start with some x naught that's down here, now my rate of change is saying to increase. When I start with the initial condition here, x prime being positive says, go towards 0, go towards it, go towards it. Hey, you know what? As you get closer to 0, go a little slower. As you get even closer to 0, go a little slower still. That's the exponential decay talking. It wants to get to 0, but it never quite gets there because the closer it gets to 0, the closer its rate of change gets to 0 too. Ooh, so it's like it wants to be at 0, but it can only asymptotically approach it, and it will technically never literally reach the value of 0. In mathematical theory, anyway. Okay, so if I start with this negative initial condition, it's going to look like this. I'm going to increase and increase and increase. But as I get closer to 0, my rate of increase is going to decrease itself. It's going to be a smaller approach, and so I'm always going to be trying to get towards 0, never quite getting there. But the point is that here's my equilibrium. My equilibrium value is x is equal to 0. And no matter where I start off of that point, things want to go towards it. So that's why in this case, x equals 0 is a stable equilibrium. That's a stable equilibrium.